Welcome. Welcome to our class. Um, welcome to class number 5, I think. Is it 5? Lecture 5. Today we're going to be going over binary trees, specifically searching, and I kind of go into sorting a bit. I didn't think I was going to go into sorting as much, but I do go into sorting. Previously, on this episode, we watched how to create linked lists, which are built of nodes, right? Linked lists are nodes. There are a bunch of nodes tied together. Each node has a piece of data, and each node has an address. So that address leads to the next node. We can slowly link a bunch of nodes together to create an entire list of different nodes with different data, right? We also learn how to create stacks and queues out of the same structure, just changing how we can push, pop, add, remove, and change where our head and tail of the structure are themselves, right? So we know how to make a node and make a structure out of nodes. I think at the end of the lecture, I described that with this node class that has one piece of data so far and one address, I hinted that what if we change this node class to have one piece of data and 2 addresses, right? I briefly hinted at this, and this is the entire structure of how we create binary trees. So let's look over here. What is a binary tree? So first off, this image on the right is a binary tree. This is just a general tree. It looks like your family tree. So your family tree is an example of a binary tree. Not an example of a binary tree, it's an example of a tree where you have a bunch of nodes which are each individual, and you have children, you have parents, you have children, you have children, you have children, until like forever. Does anyone have a family tree that they've seen? All right, I've seen like two of the supers have had one, and the one was like since 1850. And there's like 6 or 7 generations. I think mine is like 8 generations. I think I've seen it like once in my lifetime, and my mom stored it somewhere away. But family tree, same thing where we have a bunch of nodes of data, and they're all connected via parents. The phone book. We kind of talked about the phone book previously being like a tree, where we're talking about runtime, where we could do like a binary search on a phone book. Same concept where it's already sorted, but it's sorted linearly. Let's go into, I'm going to go into this first. The node class. So as I talked about, the node class originally was one piece of data, one address to a node. So addresses to the next node in the linked list. Here, we're creating a same piece of data, but a left and a right node. So we have 2 nodes. This makes it so that we can have one piece of data with a left side pointing to a node, and another right side pointing to another node. Saying we can keep going down, where we create 2 nodes ideally for each node. We do have some nodes with nothing, and we'll talk about that in a second. But we can slowly address to other nodes and create a tree out of this. Does that kind of make sense? We just added one line basically to our class. If I go back, this is the vocabulary of what I'm going to be talking about today. This is just to help you understand what I'm talking about throughout the lecture. I'm going to reference all of these things. A here is my root. This is my root. This is the beginning of my tree. It's the same like how a linked list has a head. This is the start of my tree. I always start at the root, and I always should end at the root, technically. We have a little subtree here where we have a parent node. So these are all nodes. D is a parent node to H and I. H and I are the children of D. So every node has children ideally. So A is the parent of B and C. B is the parent of D and E. D is the parent of H and I. So these are children to my node D. This is just a subtree because it does represent a tree itself. C is the parent of F and G, but F and G are siblings. They are sibling nodes that have the same parent. Lastly, we have the leaf node, which is any node at the end of our tree. So we have a bunch of branches coming off our tree. Hello, sir.
Can I just like sit down?
Yeah, you can sit down. So we have leaves, which hold the end of our branch. So they're the end of our branch. They don't have any children. They're just the end. These levels are familiar. We've seen these levels before. Does anyone remember where we see these levels? We saw them in our, I think, our first lecture. It was when we talked about the runtime of merge, merge sort, where we can break them into levels, where we have 2 items, we have 4 items, we have 8 items, we have 16 items, so on. So these are the levels of our tree. The first level is just the first node. The second level is the second node. We kind of go through things. We can look at things by level as well, and that's just where we're at in the tree. All right, cool. Cool. So let's talk about some examples of structures of trees. These aren't, every tree is not like this, but this is just an example of how we construct our tree when we build them. So first off, we have a full binary tree. A full binary tree, every node has 0 or 2 children in it. So in this first case, 18 has 2 children, 15 has 2 children, and 30 has 2 children. Each of those have 2 children, but all our leaves have 0 children. There is no node that has 1 children alone, right? That doesn't have 1 child. There's no 1 child alone. Same for this, 18 has 2 children, 15 has 2 children, 40 has 2 children. All these leaves have 0 children. There's no 1 node. And this is just a full tree. Full tree just being everything has 2 children or no children. That kind of makes sense? Cool. Now let's talk about a complete binary tree. This is a little complex. A complete binary tree says all levels are filled of nodes with the exception of the last level. So let's start off with that first point. All levels are filled of nodes. 18 here is a full level. 15 and 30 is a full level. 40, 50, 140 is a full level. And that we have, for each level, we have 1, 2, 4, ideally 8, 16 nodes. Every level is filled out, no matter what. Does that make sense how that's a complete tree? Now we can add on to that and then say, if we add more nodes that make it not a full level, the last level must have all nodes left in the leftmost position. So we add 3 more nodes to this exact same tree. We must put them in the leftmost positions to make it a complete tree. Where 8 is on the left, then 7 is next to it, and 9 is next to that. Let's do an example by building that actually out. Let's have an example of how we actually build that out. So, if I start off with 18, right? I start off with 18 at the top. This is a complete tree, technically, right? Its level is filled. The first level is filled. Now, if I add 15 onto this, I'm going to add it on the left side, because we're going to go left to right, and this is technically also a complete tree. The first level is filled. The last level is the exception, where we have the leftmost position. That make sense? Now we can add 30, still a complete tree. And I can add 40, I can add 50, still a complete tree. All throughout this, we are all making a complete tree every single time. We slowly add from left to right. Now we add 100, we add 40, a complete tree. We add 8, still a complete tree, because we're adding from left to right. So we're inserting our items on the left side to the right side. So it kind of makes sense how this is actually built out. Yeah, more or less. Cool. So we can build our tree like this. We don't have to. This is just one option for how we can build our tree. This tends to balance our tree very evenly depending on the level. So it balances left and right side to whatever level we're on. And I'll explain more why balancing is pretty useful later. We can also have a perfect binary tree, where this is a perfect triangle. We're always going to have a complete tree. All nodes have 2 children, and all leaves are on the same level. So all nodes have 2 children, all leaves are on the exact same level. It's a pretty simple tree. We have also a degenerate binary tree, or pathological binary tree, because why would you do this? What is the point for this, right? This acts just like a linked list, and that it's linking a node to a node to a node to a node. There's no split in nodes. It acts the exact same. It has the same performance as a linked list. This can happen if we don't balance our tree. If we just let our tree be built, this is a possibility. Using the other perfect and completed methods, we can balance our tree if we want to. Does that kind of make sense? How we can slowly balance it by adding things to the left to right? Now we're not heavy on one side, not heavy on the other side. This is very heavy in one case. So these are all ways of creating trees. We're not sorting it, we're not searching it, we're just creating a tree. Now let's search through the tree. So still on an unsorted tree, so let's think about if I have my ancestry family tree, right? I have my family tree. It's built from top down. I have 8 generations of people. I don't know who that top person is, but I don't know if I have a Larry in my family. Maybe I'm looking for some guy named Larry. Looking for Larry Poole. I don't know where he is in my family. I have to start by searching through that tree somehow, right? I have to look through every single individual in that tree. And in Java or any computer science language, there are 2 main ways to do that. The 2 main ways to do that are, we could do breadth first search or depth first search. So BFS for breadth first search, DFS for depth first search. These are 2 very common topics of how we search through trees. Depth first search or breadth first search. Let's start with that. I'll describe more on another slide. Breadth first search. The overall idea of it is that if we have a tree, we're going from level to level to level to level. We're always searching from level to level. Once one level is complete, we move on to the next level. Once that level is complete, we move on to the next level. We slowly go level to level. Depth first search goes down the entire branch until it reaches the leaf. Once it reaches the leaf, it comes back up, searches another branch. Goes back up, searches another branch. And it slowly goes to the depth of the tree, how long the tree is, then comes back up and does another depth of the tree. So level, horizontal versus a vertical structure. And I'll do an example of that. So breadth first search, if we have this tree on the right, we have A as a parent of B and C, B as a child of D, and C as the children of E and F. So that's our tree. We can see that breadth first search, you search through the breadth of the tree at the highest elements before working your way down. So we start off at A. We check, is A Larry Poole? A is not Larry Poole. We finish this level, so we move on to the next level. We check B, is B Larry Poole? No. C? No. We finish this level, we move on to the next level. We slowly go level by level by level. And there's a good reason for this, and I'll explain why and how we actually do this later. But the concept of breadth first search is that we go level by level by level. Does that kind of make sense? Cool. Now depth first search, we go through the full depth of the tree or the branch until you've reached the bottom or the leaf. Then you go back to the top and start again. So here, instead of going from level to level, we're going to go from depth to depth to depth. We're going to go, and here's the right here, we're going to go A, B, D, which is going to go all the way down the depth of the left side. We're going to come back up. We're going to go A, C, E, because we're still going right to the left. Always do the leftmost stuff first. And then we work down our right side. We slowly go down the length of the entire tree. And we come back up and go back down the other side. I'll explain how this works in a bit, but the concept of this is going down the branches of the tree. Make sense? Good? Cool. 2 concepts, pretty similar. So let's talk about what the differences are. So, we talked about previously, we've used stacks and queues, we've talked about some examples about it, but this is the prime example of using a stack and a queue, why we use them and why they're so great. A breadth first search uses a queue. We use a queue for breadth first search, and I'll show you. Depth first search uses a stack. And those are very key concepts and why these things become so fast. The time complexity is the exact same, where it's O of V, which is our vertices or our nodes, and E is our edges. So edges meaning the connections between node to node, so the address. So depending on how many nodes we visit and how many edges we pass through, that's our time complexity. Their average case is the exact same. Breadth first search searches through siblings horizontally versus before going to children. Depth first search goes to children and then come back to siblings. Just a conceptual thing. 4, breadth first search is really good when you know your data is close to the top. When your data is close to the source, it's really good. Of those different data structures I talked about at the beginning, the different types of trees I talked about at the beginning, when is breadth first search good?
When you have data closest to the top.
When data is closest to the top, but which of those tree structures?
The complete binary.
You think the complete binary? Anyone else on the other ones? No, we're all good there. So the complete binary or the perfect binary. Those are all trees that are all going to generally be triangular shaped. They're going to be balanced from left side to right side. When is depth first search good?
The degenerate.
The degenerate binary tree, right? Because you have one long strand all the way down. You might have a couple other long strands, but they're going to be long. Meaning you're going to try to go from one down straight through the other versus level by level. Does that make sense? When these two can be good? They're very good overall in comparison to each other. They complement each other really well because they do opposite things. They have the exact same runtime. There's no good way to tell you like which one's better than the other. You just need to kind of, by application, you can choose which one to use. They both have strengths, they both have weaknesses, they're very equal. Does that kind of make sense? They're equal, they do what they do. So let's go into actually using a queue to do breadth first search. This is a little more thinking about what is a queue again?
First in, first out.
First in, first out. It's a line, right? So if we have a line, we're going to draw a little queue here. I made an awkward queue looking thing. This is our queue. So when we use a queue, it says when a node is visited, add the children to the queue, and pop off the visited node. So breadth first search is level by level. We're going to start with A. We're going to add A to the queue. A is in the queue. It says when a node is visited, add the children. We're going to add the children to the queue. We're going to add B. We're going to add C. Now it says pop off the visited node. Well, bam, A is gone. Now we look at the next value in the queue, which is what? B. B is now my next value in the queue. So I do this guy. I say, when the node is visited, add the children. The children is D. The child is D for B. We add it to the queue, and we pop off B. But now, instead of going straight to B, we do whatever the queue says, which the next node in the queue is C. And just because we made it in a queue, we can then access C right after B. We don't jump down to B. So now we go to C, we add E and F, and we pop C off. And then we do D, E, and F. Does that make sense how a queue really makes that work? It has to work only with a queue. If you have an array to do this, you kind of can lose place. You have to use some type of iterator to go through it. But we can slowly add items and remove items depending on what we visited and what we're looking to visit in the future. So a queue really makes what this works. And that's how that works. And it explains it there more. So now let's look at how depth first search uses a stack. So for a stack, it's the opposite, right? What is the rule?
Last in, first out.
Last in, first out. So 1, 2, 3, 4. Sure. Last in, first out. So the last one in, give me the first one out. Here, we're not doing level by level. We're going to go length by length. So the way this works is a little more complicated. We start with A. We say, push a node to the stack. Visit the left node. If the end is reached, pop from the stack until the right node is visible. Only pop if the left and right sides have been visited. So let's start with A. We start with A. We add A to the stack. We look at the left node. We add B to the stack. Does B have a left side or a right side? It has a left side, so we still visit the left side. Now we look at D. Now D here doesn't have left or right, so we visited D, we can mark it off, and then we pop it off of the stack. Now I'm going to draw out what's going on here. So we go visit B, we go visit D. As soon as we're done visiting D, we go back up. Since we popped it off, we go back up to B. Now B, we check, does it have a right side? No right side, we visit the left side, everything's been visited. We pop it off the stack. We go to A. Now A has a right side. We haven't visited yet, so we can't pop it yet. So we go down the right side now. We go on the right side, we say C. We haven't visited C, so we add C to the stack. C has a left and a right side, we go down the left side. We add E. We go down the stack here. E doesn't have a left or right side, so we pop it off the stack. Now we go back to C, and C still has a right side. So we add F. We go down to F, and then we go back all the way back up to A. So we pop off F, we pop off C, we pop off A. Does that make sense of how we're able to use this stack by storing the previous parents to go back? So we store A, B, D. We can go back by popping off D, B, A. We can slowly store these things and remove them back off. This is the same concept of recursion. Where we're able to go down one side of the tree, come back up. Go down the other side of the tree, come back up. Stacks remove the ability to do recursion. We don't have to use recursion for this. Because for depth first search, we can just abuse the stack structure to be able to do this really, really quickly. For this, we should only have to use a loop that goes 6 times, ideally. It visits this node, this node, this node, then goes back, visits this node, this node, this node, this node. It should go through that same structure, and then we're popping X amount of times from the stack. Does that make sense how this can remove the ability to use recursion? We don't have to use recursion at all here, which is really nice. Just because we have a stack and because we have a queue. Good? Cool. So that's how we use queues, that's how we use stacks. Best examples of how we use these things into their best of abilities. So these were all things that we have no clue how the data looks inside the tree. We're just looking for some item. There's an average runtime of something to get that runtime, to get that item, right? Sorting makes us so much easier. Sorting a binary tree makes us so much easier. So let's do it. So sorting a binary tree, ideally we create a binary tree sorted. So we've talked about binary trees so far. They haven't been sorted. We are going to sort them. So here we have the value of 50 as my root. 50 is my root. I can look at that. The way this is sorted, the left side of the node is everything less than. The right side of 50 is everything that's greater than 50. And that goes for every single node. If I look at 17, the left side of 17 is less than it. The right side of 17 is greater than it, right? Every value is less than or greater than, depending on the node itself. So this is a picture I got from online. I have no clue how this actually looks. But this is my guess of what the array might have been looking like. So if I go through this array, we start at 50. We start at 50, that becomes my root node. We have gone through 50. Now I have 17. We look at 17. Is 17 less than or greater than 50? It's less than. So there's no node there. We're going to build a node for 17. We look at 12. Is 12 less than or greater than 50? It's less than. Is it less than or greater than 17? Less than. There's no node there. We build that node. Do the same for 72. It's greater than. We build that node. 54. It's greater than 50, but it's less than 72. So we go on the left side. Do we see how we're slowly inserting different nodes into this tree to build it out? This is how we create a structured and sorted tree. We're not going to do breadth first search or depth first search. We're just going to build it sorted so we can search through it way easier. So let's do this together.
Yay.
Yeah. Where does 63 go here?
At the top.
Very top. It is my root node, right? 63 goes right at the top. And where does 97 go? Is it bigger or less than 63?
Greater than first to the right.
Going to the right side. Fantastic. Nice job. 102.
Go to the right twice.
Right to the right, right? 44. Is it less than or greater than 63?
Less than.
Less than. It's going to go the other side. 75. Is it greater than 63?
Greater than.
Is it less than 97?
Less than.
Yes.
So it's going to sit right there, right?
Left.
12. Where does that sit?
Way.
Way left. It goes less than 63, less than 44. 12 goes to the left of it. Where does 55 go?
Right node of 44.
Left.
Right at 44, so it's less than 63, greater than 44, sits right there. 49.
Left, right, left. Left, right, left.
Left of 63, right at 44, left of 55, sits right there. It's less than. 2, where does 2
All the
go?
way to left.
All the way left. You can see a little pattern of the small and the biggest values, right? 2 is going to sit far left. 113,
All the way right.
all the right, it's our biggest value. 111,
Right, right, left.
so it's bigger than the 102, less than the 113,
Left.
so we sit left side. 99, 99 is bigger than 63.
Right.
Right.
It is bigger than 97. It is less than 102. Sits right there. Do we see how this is going?
Mm-hmm.
Making sense? 51 is a little weird.
Left, right, left.
So less than 63, bigger than 44, less than
Oh, no.
55, bigger than
Right.
49.
Oh, okay, got it.
You see that?
Oh.
Now it's 46. Same thing.
Left.
Less than 63, greater than 44, less than 55, less than 49. Make sense? We're slowly doing this out. And that anything we add to this, if we keep inserting more numbers, it will stay sorted, no matter what. We can go down this and be like, this is less than, this is greater than that, there's less than that, there's less than that. We can keep going down until we see a perfectly built out sorted tree. So we can build this sorted, which is really nice. We have this array. We just have to insert this number, insert this number, insert this number, and we keep inserting numbers over and over again until we build out this tree. So we'll talk about how we actually insert these things. Before we get to that, what happens if we add duplicates? How do we handle duplicates? There are two ways to handle duplicates. The first way is we can make a rule to always insert it on the same side of the tree. So here I've chosen to always insert my node to the right side of the duplicate. So for 55, I've chosen to write 55 to the right side of this duplicate. If I have another 75, it'll be right on the right side. If I have another 51, it'll be on the right side. Now if I chose to put this on the left, if I chose to put 55 on the left side, and every other duplicate on the left side, it would go over here to 49, bigger than 51, it's going to sit on the right side of 51. Not quite in the same space, but we're always keeping up with the same rule. And we'll always find it in the same ideal space. Yes?
So does this count as a degenerate one because it's not complete?
Not quite. This is just a general binary tree. Degenerates are like straight down, one line. This is just a binary tree.
Okay.
There is no, it's not perfect, it's not any of those, it's just a binary tree.
Okay.
But we don't have to make it those things. Those structures are purely for unsorted binary trees,
Oh, okay.
where we can then balance them to make it easier to do breadth first search and depth first search. Here, we don't have to do breadth first search or depth first search. Because it's already sorted, we could just do a binary search, right? Where a binary search is very similar to merge sort, where we can split this down the middle and be like, where is 32 on this number graph? I look left at 44, we don't have a 32. But do you see how we don't have to use breadth first search or depth first search for this? We could just use a binary search that splits things in half, and we're already cutting it in half. We built it in whatever time it takes to insert items, and we can search through it in log n time, because it's half of the time because we're splitting in half over and over again. Does that make sense? So we wouldn't use breadth first search or depth first search on that. All the stuff previous to this was unsorted trees. Now the other way to do duplicates is we can change the node's data structure to hold an extra value. So node has data, it has 2 addresses. We can add a 4th thing that is weight, where weight is just integer saying how many of this value do we have. So here, we added 55. We added 2 to add a second value there. So we have 2 55s. It is a weight of 2. Anytime we reach that node, we know there are 2 55s. It really doesn't matter what the weight of something is, unless we're printing it out. If we're just searching for an item, if we have it, we can see that we have the item. Searching for it is very easy. Does that kind of make sense, where we add a weight to our node class? Cool. You can make your own tree if you want. I'm not going to go through it. I'm kind of done already. Inserting things are very easy. Removing things is very hard. If you think about, what if I remove 97? It breaks a lot of things, right? It breaks a lot of things. You have to go through the process of actually building that back. So removing is pretty hard. It's a whole problem on its own. I would definitely look into it if I were you. Trees love recursion. Just like how arrays love loops, trees love recursion. Do we know why? What is a reason why trees love recursion? They're going hand in hand. Yes, Peter.
Because when you search it, you kind of do the same thing until you get the number.
Kind of, yes. So I think you're thinking about if I were to go back, I can search all the way down something, and then I can go back up the tree, and then go back down and back up. And this process of going down a tree and returning back up it is part of this recursive process. So we're calling recursion over and over again to traverse the tree and search through the tree. This is similar with the stack, where the stack takes the place of recursion. It goes down, We push elements to the stack, and we pop from the stack to go back up. Push elements to the stack, pop to go back up. Same concept of recursion. We're just using stack instead. So trees love recursion, so let's look at some recursion. I know John Paulo loves this stuff. On the left, we have some insertion code. So to build the tree, we just have to use a special insert, recursive insert for building the tree. On the right is the tree we've seen before. We're going to try to insert the value 46. To insert the value 46, we can start off at our node of 63 for our root, and our key is going to be 46, the value that we're trying to insert. So if we start at 63, we can say, is the root equal to null? Is this null? This is not null, it's not empty, there's a value there. Otherwise, we could say, if the value is less than 63, go on the left side. If the value is greater than 63, go on the right side. Now we're slowly going down, so we go to the left side. And it says call insertion on this new root, which is 44. So now we insert on this root. Is 46 bigger than 44? It is.
Yeah.
So it goes here. It goes 55. And I say 55. Is it empty? It's not empty. 46 less than it? It is. 49. 49 is not empty. We check if it's less than or greater than it. It's less than it. And now we get to an empty node here, where there's nothing there. And this is my root. So it says, is the root equal to null? In this case, the root is null. There's no value there. Since it's null, we add a new node and make it equal to 46. And then we can go back up the tree, returning our roots all the way back up. Does that kind of make sense? Yeah? So we're just going down the tree mostly for insertion. If I were to ask you, what if I wanted to print out every single number here in number order, so from lowest to highest? How would we do that? We'd also use recursion. But do you guys remember that example I had where I would walk to my house taking a step each way?
Oh yeah.
I grab my keys and I come back? Same exact concept. Or if I look at this next slide, whoop, too far. On this next slide, here, I have that exact same concept. Here on the left, I'm going to my house. I'm taking a step to my house. I'm taking a step to my house. I'm taking my step to my house. Until I get to the farthest left, then I print out my value. I print out my value. I keep coming back. The walking back is this right side. Where I go left to my house, I come back to my right side. So here, let's start at 63. 63 is it says, do the same thing on the left, and then print me out, and then do the same thing on the right. When we pause and we go do the stuff on the left first. So it says, go do stuff on the left for 44. Go do the stuff on the left for 12. Go do stuff on the left for 2, but there's no stuff on the left. So since there's nothing on the left, it prints out 2, tries to do stuff on the right, there's nothing on the right. So we go back to 12. We print out 12, and we try to do stuff on the right, there's nothing on the right. We go back, we print out 44. But this stuff does have something on the right, so it goes right. Then we call, do stuff on the left for this guy. Do stuff on the left. We print out 46. We go back, there's no right, we go back, do the right. Print out this. And we keep going all the way back. Do you see how we're slowly traversing the tree? And I'll draw it out. We should be going like this. We should go this way, down here, up here, back. That is the traversal of my tree. Beautiful. That was absolutely ugly.
It is abstract art.
It is abstract art, man. There's some cool graphical art that people create that is similar to this off of data structures. But this is how I traverse a tree. And we take steps to go to the left side, we pull back until we see a right side, go to the right side. Pull back, go all my full right side. So trees are breadth first search, depth first search. You'll look at trees more. That is all I actually had. Next will be graphs, and graphs are super cool. Graphs are trees, but all the nodes can go back to each other and connect to all of each other and everything else in between. If you think about the easiest graph to think about is your social network. If you have an Instagram, you're friends with somebody, hey, you're a node, your friend's a node, you're connected, but you also have this other friend that is connected to that node, friend, this friend. I'm gonna build a beautiful graph. So is that? Is the internet, yes. That works. Now you're looking at networks. And that is a graph on its own. It's also the Amazon Service Delivery Driver, where he's going to each house There's a bunch of houses, a bunch of roads. How does he get to each house the fastest? What's the fastest route? All uses the graph. Cool?
Yeah.
Reminds me of, I was about to say that thing, binary tree, right?
Yeah.
How it looked, how you like made the visualization of it. Kind of reminded me of like Dijkstra's algorithm.
It's exactly what
Yes.
it is. It is Dijkstra's algorithm.
Yeah.
You're doing that on this stuff. Yes.
Are we gonna learn Dijkstra's algorithm?
On
or-
graphs, yes. That's what graphs are, right?
Yeah. Hell yeah.
Hell yeah. Good. It is. Dijkstra's algorithm is one of the biggest algorithms for graphs and all that, right?
Are we, will we also learn star?
I don't know. We'll see. I haven't made the slides yet. We're there. I love it.